plan accordingly. So that homework quiz would probably just cover the stuff from the first lesson, right, from the previous lecture. Cool?
Just that display of water splat at me.
Water dries.
Water dries.
I think I deserve the golden rule to treat others as human beings. So he just treated me like that, and I get to treat him.
As soon as you walk out the building, you are free to do whatever you want. All right. So today we're going to finish up chapter 13. In chapter 13, we've been talking about finding the zeros for polynomials, right? So last time we looked at how to do this purely algebraically, where we could use like quadratic factoring, greatest common factor in kind of combination to still find the zeros for polynomials. And we looked at doing polynomial division. Today what we're going to do is connect this idea of polynomial division with polynomials that we can't factor using just greatest common factor and quadratic techniques to kind of extend the set of polynomials that we can find zeros for algebraically. So that's the plan today. So we're going to start with a mess of theorems here. So the first theorem is called the remainder theorem. And this one says if I have some polynomial f of x and I divide it by some polynomial x minus k, then the remainder of that polynomial is f of x minus k. So, for example, if we wanted to apply this, it says find a f of 2 using the remainder theorem. So I know that to do that, like f of 2 is like my x, or f of k, and like my f of x is this guy. So what is my x minus k then? What is my x minus k then? What is k? K is 2, right? Well, f of k, f of 2. So k is 2, right? Okay. So what I'm going to do is I'm going to go ahead and do this division. And I know that the remainder from this division should equal the same thing as f of 2. So what times x gives me 2x squared? Well, 2x. I distribute those to both places, subtract down, bring down the 4. Won't distribute that. Subtract down, I get 2. So should be f of 2 should equal the remainder, 2. Let's just check that. So f of 2, if I did this via substitution, should be 2 squared minus 5 times 2 plus 4. Well, that's 8 minus 10 plus 4. That is indeed 2. So sure, that seems to work. Now, ideally, the substitution is typically easier than the division, right? Typically, we'd want to go this way and use the substitution to find the remainder for a division problem. Plugging the numbers in is typically easier than doing that long division process, right? Yeah. So that kind of becomes the foundation for the synthetic division idea that we've seen earlier. We'll kind of circle back to that in a moment. Our next theorem is called the factor theorem. So in particular, what kind of remainder are we most interested in if we're trying to factor polynomials so we can find their zeros? Well, a zero remainder, right? And that's all the factor theorem tells us, is that if I have some factor x minus k that gives us remainder 0, or that f of k is equal to 0, then that's a factor, right? Which is great. Let's see that kind of happen in practice. So the directions say use the factor theorem to show that x plus 3 is a factor to, or is a factor of 6x cubed, yada, yada, yada. So x plus 3 is my x minus k, right? What is k then? K is negative 3. So f of negative 3 should be 6 negative 3 cubed plus 25 negative 3 squared plus 16 times negative 3 minus 15. So let's see, what is that? That's 27 times 6 is 160, negative 162. And then 9 times 25 is 225. Minus 48 minus 15, that indeed is 0, right? Then that's, so by the factor theorem, we know that x plus 3 is a factor. So what does this tell us then? It tells us that this polynomial is equal to x plus 3 times something. We don't know what that something is, right? This is the beautiful part about using that synthetic division, is that it not only gives us that remainder is 0, but it also gives us the other half of our factoring problem, right? Again, remember that these numbers underneath are remainder, constant, x coefficient, x squared coefficient, etc. Everybody's okay there? So this is going to kind of lay the foundation for a factoring technique we can use when I can't factor as a greatest common factor or a quadratic. It gives us something else we can do, another tool. The issue is, how do I find a starting spot, right? I need to figure out, like, okay, what could be a factor, right? If I have some things that might be factors, I can check them using synthetic division. And if I find one that gives me a remainder 0, hey, I found a factor and I can do some factoring with the synthetic division. But how do I find these guys to start with? Well, our first and best tool that we're going to have is called the rational zeros theorem. So what this says is that for some polynomial with leading coefficient a sub n and constant term a sub 0, any possible rational 0 has to be of the form p over q, where p is a factor of the constant term a sub 0 and q is a factor of the leading coefficient a sub n. So those are the only possibilities that we can use for synthetic division, are these things that come from this rational zeros theorem. Let's do a couple of examples, kind of practicing that. So this says make a list of every possible rational 0 for the polynomial f of x equals yada, yada, yada. So I'm going to start first by making my list of p's, which come from the factors of the constant term. So what are the factors of 4? 2. 1. 4. Well, we're halfway there. There's still 3 more. If you can think of one of them, you'll get the other ones.
1/2.
Nope. negatives. I thought that saying there's 3 more would have been the hint that you needed, since we had 3 numbers up initially. It's not cheating though, although it is like tricky, I guess. And then Q are going to be the factors of the leading coefficient. What are factors of 3? Hi, Talika. Okay. Andrew, it's for you. I think you knew this was coming.
Yeah.
Okay. What are factors of 3?
3 and 1.
Come on.
Positive, negative.
There you go. Plus or minus 1, plus or minus 3. Thank you. Okay. So my list then of possible rational zeros are going to be 1 over 1, 2 over 1, 4 over 1. You're welcome. And then 1 over 3, 4 over 3, and 4 over 3. Everybody's okay with how I came up with the list? Now, if there was, say, instead of like 3 P's and 2 Q's, what if there was like 6 P's and 6 Q's? How many things would it be on our list? Dude, there's 36 things on that list. That's just super annoying to write, right? Alternatively, what would be okay is I'd also allow you to write your list this way. Just for the sake of quickness, right? That's way faster to write that than to write out like maybe if there's like 36 possibilities, like, oh my God, give me a break, Mr. Cook. I got to write out 36 of these things. Yeah. That's way easier, right? All right. Now, there's still, there's 6 things on this list, but there's really 12 because of the plus or minus, right? So that means there's possibly, I'd have to check 12 things before I found a remainder 0. Woof! This next theorem here we can use to kind of cull that list down a little bit. Now, this next theorem was something that as a student, Mr. Kulik, when he was in his Algebra 2 class back in like 1997 or something, this was super useful to him. Much less useful to you guys now because of the technology difference between when I was a student and when you are a student. But this theorem says for some polynomial with positive leading coefficient, and we divide by k using synthetic division. If k is greater than or equal to 0, and every number in the bottom line is non-negative, then that k is an upper bound. So if I did this synthetic division and I got the result where everything on the bottom line was non-negative, I could eliminate from my list everything that was bigger than that k. So it would allow me to cross some stuff off of this list without having to check it manually. Ideally, I use something from my list and do this check with it. So I'm killing like 2 birds with 1 stone. And then if k is negative and every number on the bottom line alternates from negative to positive, I should say non-negative to non-positive, then k is a lower bound. So everything less than k I could cross off that list. Now, for you guys, would probably not ever use this in practice, although there are homework questions that ask you to do this, and possibly Mr. Kulik would ask you to do this on the test. We'll explain what you would do in practice instead of doing this, because you have a much better method than like this kind of guess and check and making, like eliminating some choices. But this example problem says, show that every real 0 for the polynomial f of x lies within the interval -5 to +4. So to do that, I'm going to do a synthetic division with -5. So if I look, this is k less than 0. So I need alternating between non-positive and non-negative. I see that So I know that -5 is a lower bound. So none of my zeros could be less than -5. So if I went back to my possible rational zeros, I could eliminate all the zeros that were less than -5. Those couldn't be actual zeros, right? All my possibilities. And then we'll do a synthetic division with 4. So here we're looking for, I have a k that's positive. So I'm looking for non-negative on my bottom line. If I look positive, 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 that's good. So I know 4 is an upper bound. So if, again, I went back to my possible rational zeros, I could eliminate everything that was bigger than 4 from my list. And that was something Mr. Kulik would have used as a student to like cull my list down, particularly if I had like 70 or 80 possibilities, yuckarooskies. Like if I can get like, if I can kill 5 or 6 of them at a time with one synthetic division, that's great for me. Now for you guys in practice, we have a tool much better than this. What can we use? Your graphing calculator. Specifically, if I graph the polynomial and look for the x-intercepts, that'll tell you exactly where the real zeros are kind of at, right? So let's do an example where we use the calculator to kind of do this whole shebang, right? So I know that from our previous lesson, because the degree of this polynomial is 3, oops, not at least, that's at most. I have at most 3 zeros, right? Could be less, but it's at the most it could be is 3. My possible rational zeros are going to be my factors of 30 over my factors of 6. 30 is a rough one, guys. It's a lot of factors of 30. And 6 is no picnic either. Everybody's cool with that?
Yeah.
Now I'm going to go to my calculator. If you have your calculator with you, I invite you to take it out and follow along. Into my calculator, I'm going to type this polynomial exactly as it looks into the y equals. Now, again, should go without saying, but super important you're able to type your equation in correctly. Because we're about to look at the graph and make decisions based on the graph. If you make a typo here, like all your decisions based on said graph are going to be wrong because you're looking at the wrong graph. If things don't make sense, what's the first thing you should check? Yeah, make sure you typed in the equation or the polynomial correctly, because if you screw that up, boy howdy, it's, you know, nothing's going to make a lot of sense afterwards. All right, so I got this guy in here. Now I'm going to set a window. What is the smallest zero from this list of possible rational zeros? I'm going to use that for the x-min. What would be the smallest number on this list? The smallest number on that list. Yeah, negative 30. Good. What's the biggest number? Positive 30, right? And really all I care about is the x-intercept, so I'm just going to leave my y-min as negative 2 and my y-max as positive 2. I'm going to hit graph now. Take a look at where my x-intercepts lie. So it looks like to me all the action is happening between, say, like -6 and +3 maybe. You guys buy that? So I'm going to go ahead and reset my window so I can get a closer look. I'm going to do -7 to +4 because I care how the graph is also crossing the x-axis because I'm looking for bend, bounces, and straights. So I want to see a little bit on either side of -6 or +3. So if I look, this looks like -6. That's a straight. That looks like, well, let's look at my list. It's less than 1, right? So probably +1/3. That's probably what that is. And then this would be 2.5 on my list. That's 5/2. And each one of those appeared to be a straight, which is giving me 3 zeros, right? Which is what I'd expect. I can't have more than that. Again, I want to confirm that what I read off the graph is actually a possibility. Because if the number I read from the graph is not on my list of possible rational zeros, that would tell me that it is irrational and not something I can use a synthetic division with. So I have to be very careful here. Now, just because 1/3 is on my list, I made an estimate that that was 1/3. I guessed to some extent, right? It could be that that's an irrational number that's just really close to 1/3. I don't know for sure. Which of these 3 numbers do you think I should start my synthetic division with? -6. 1, it's not a fraction, which just makes life easier. 2, if I looked at my graph, that's the one I was most confident that it's actually -6 because it passes like right through the tick mark. The other ones were kind of an estimate, right? So let's start our synthetic division. Ugh. There we go. I got remainder 0. Yay! All right. Just to recap, what does this mean? Well, it meant 6x cubed plus 23x squared minus 83x minus 30 factors to x plus 6. And again, I get that because -6 gives me a remainder 0 times 6x squared minus 13x minus 5. How do I get that part? The numbers under the bar, or under my synthetic division bar. Does everybody feel okay? Now I have 2 choices. Notice that my factoring resulted in a linear polynomial and a quadratic polynomial. Do we know how to solve every single linear equation? Yup. Do you know how to solve every single quadratic equation? Yup. So right now, even though this might be able to factor more, I can just go about setting it equal to 0 and solving these 2 things separately by applying the 0 product property. So I get -6. And then here I'm going to use the quadratic formula. Now I know that this thing could be factorable, but since the leading coefficient is bigger than 1, if it is factorable, it's going to be kind of a pain in the neck to factor it. I can't just look at it and factor it quickly in my head. It takes a little bit more effort than that. I don't really want to do that much effort. I'm just going to plug it into the quadratic formula if I don't see immediately how to factor it or how to solve it. So the quadratic formula again for ax squared plus bx plus c equal to 0 is negative b plus or minus square root of b squared minus 4ac all over 2a. If you don't have that memorized now as a high school student, you should. Every high school student should have the quadratic formula memorized. Like that is something that people will expect that you have memorized if you walk into another math classroom. All right, so here we have x equals negative of negative 13 plus or minus negative 13 squared minus 4 times 6 times negative 5 all over 2 times 6. Negative of negative 13 is positive 13. 13 squared is 169. Negative 4 times 6 times negative 5 is 120. 169 plus 120 is 180, or is 289, and the square root of that is 17. 13 plus 17 is 30. 30 over 12 is 5 over 2. 13 minus 17 is negative 4. Negative 4 over 12 is negative 1/3. There we go. And there's our 3 answers. I know, I did the arithmetic really quickly, and you're like, how are you doing it that quickly? Well, part of it is, this is the 3rd time I've done this problem, so I remember all the things that happened to it, but like the arithmetic isn't that bad. You should be able to do this kind of stuff in the head. The only part that would have been really challenging was the square root of 289, recognizing that that was 17, but, you know. Okay. So your question at this point should be like, Mr. Kulik, those are just the x-intercepts. Like, why can't I just use the calculator and find the zeros? Like, why can't I just do that? Why do I have to do this stupid process here? Well, 2 reasons. One, if I wanted the exact answers, there's a possibility of getting an irrational solution, and I wouldn't be able to get like 1 minus the square root of 2 out of my calculator. It'll give me a decimal approximation. And to that you say, okay, fine, but like, what if a decimal approximation is good enough? What's the point in doing this? Well, here's the big point. Your zeros might not be real numbered. They might be imaginary. And if they are imaginary, you will never be able to get them out of the calculator. We'll have to do this. Guess what we're going to handle in section 13.4? That specific situation if we get imaginary results. So we have 2 little theorems to start with. So you remember at the beginning of the lesson, we said that the number of zeros is at most the degree of the polynomial. And I promised you that we're going to update that theorem and make it a little bit better. We're going to do that right now. So this is the complete statement. If you have a polynomial of degree n, that polynomial has n zeros, provided you're counting both real and imaginary, and that you're counting the multiplicities. So if you count both of those things, you're going to get exactly n zeros. So if something's used more than once, you have to count it the same number of times it's used, and you have to count the imaginary pieces. But if you count all that stuff, you get an n every single time. That's nice, right? Tells us if we found it all. The second piece that we're going to use, or that's going to be handy for us, is called the complex conjugates theorem. And what this theorem says is that if we have a polynomial with real coefficients, and we have a zero of a plus bi, so an imaginary zero, we necessarily also have to have the zero a minus bi. It's conjugate. Essentially, these imaginary solutions are always going to occur in pairs. Okay, you're never going to get an odd number of imaginary solutions unless you had an imaginary coefficient, but you'll never have that in a class like this, so you don't have to worry about that possibility ever happening to you here in this class. The other place where we can apply this complex conjugates theorem is in building a polynomial from its zeros. So let's look at an example of doing that. So let's say we want to write a polynomial that has the lowest degree possible and has the zeros 1, -3, and 1 plus I root 2. Well, right away, from the complex conjugates theorem, if I have 1 plus I root 2, I also have to have 1 minus I root 2. Everybody's okay with that? That we have to have the conjugate pair for it? Now what I'm going to do is I'm going to take each of these zeros and translate them into a factor. So if I subtract 1 from both sides, I get x minus 1. I add 3 to both sides, I have x plus 3. I'm going to subtract the entire complex number in one shot. So I have x minus the quantity, 1 plus I root 2. You'll see later why I want to do it this way, but it tends to make the algebra a little bit simpler to do that as one chunk with a quantity around it than each piece separately. Everybody's okay that I've turned these zeros into 4 separate polynomials? No? Oh, but you see what I did though, right? Yeah. Okay. Now I'm going to just multiply all 4 of them together. Since they all are equal to 0, if I multiply them together, they're still going to equal 0, right? Everybody agree? And I know that the product of polynomials is itself a polynomial, right? So right now I have a polynomial that has exactly these 4 zeros. My final steps would just be to FOIL this out. So typically when I do this, I'm going to group the conjugate pieces together and FOIL those, and anything else that's not in conjugate pairs I would FOIL together also. When I FOIL x minus 1 times x plus 3, I get x squared plus 2x minus 3. When I FOIL this guy, I'm going to get x times x. That's x squared. I'm going to x times negative 1 minus I root 2. And when I FOIL this, I'm going to get minus x times 1 plus I root 2. And then when I multiply those two guys together, negative and negative makes positive 1 plus I root 2 times 1 minus I root 2. So far, so good. I'm now going to distribute the negative x's through there. And then over here, hopefully we can recognize that this looks like a difference of 2 squares. Like an a plus bi times a minus bi. And I know then that's going to, if I FOIL that out, I get a squared minus b squared, right? If you didn't recognize that and you FOILed those out, you'll end up at the same spot of just a little bit extra work. But, my life, I'm looking for shortcuts, right? Work smarter, not harder. So far, so good? Okay, if I look here, I have a positive I root 2 and a negative I root 2x, so those can cancel out. I have a negative x and another negative x, that's a negative 2x. 1 squared is 1. I root 2 squared, well, I remember if I square a product, I square the factors. Who remembers what I squared is? Nope. It's negative 1. And what is the square root of 2 squared? You mean just regular 2, right? So 1 minus negative 1 times 2 is 3. And then this guy just is going to come down for the ride. And now I'm just going to FOIL this guy out. Oh, Mr. Kulik. It's like, I can't help it, guys. It's just like foiling. Blah, 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 blah. So let's see. I have an x to the fourth. Those guys give me 0. I have 3, -1, and -4 x squared. 12x minus 9. That should be my final answer. Here's the good news for you guys. Here's the good news for you guys. Come test or quiz time. That's enough for me. Why is that enough?
Because you don't want to grade that.
Because everything afterwards is previous skills, right? It's just foiling. It's just foiling and keeping track of stuff. And it's just time consuming, right? On a test, it's timed, right? Can I ask you to do, why would I ask you to spend 10 minutes doing a problem that's using skills from like Algebra 1 and Algebra 2, right? Like, why would I ask you to do that? That's an appropriate Algebra 2 problem when you're learning those skills for mastery. Here, the stuff that I'm teaching you is what we use to put that thing together. That's the part that I would want. When you got it into like something that's a polynomial, right? Like that right there is the product of 4 polynomials. That's a polynomial. Okay. That's good enough. Go. Emily. Sure. Marissa.
But like,
Marissa.
wasn't this
Miriam.
whole thing algebra 2? Like, I could have sworn we did that whole 0 thing.
Yeah, you probably have.
Oh.
But I'm just like, I'm not teaching foiling here,
Right.
right? I don't want you to spend 10 minutes foiling. Like that's not testing
Same.
anything that I want you to be doing. You don't want to be doing it. Let's not complain about it, right? Okay. Everybody's happy that stopping there is good. I would agree, right? Nobody wants that. All right. Let's get back to finding these zeros now, right? Now, if you were like in the honors course, I would expect you to FOIL that thing out, but they're capable of moving a little bit faster than you are in a test setting when doing detailing, going through details like that. But like, I'm just more interested in getting to the stuff that's like, I think using more higher level mathematics skill than like a really tedious long foiling problem where there's like a million opportunities to do something dumb. All right, find all the zeros. That means complex and real for the function. So we start. Fundamental theorem of algebra tells us that we have exactly 3 zeros. Our possible rational zeros are going to be factors of 36. Ooh, there's so many. Woo! Over the factors of 1. Then we go to our calculator. Type in my polynomial. Reset my window, -36 to +36. Hit graph. Looks like everything's happening here around maybe -3 or -4. So I'll just reset my window. So it looks like that's a -4. I have a straight. That's 1 real 0. I'm supposed to have 3 though. Where are the other 2? If I can't see them on my graph, they have to be imaginary. Okay, well, I have one number that's the -4. Let me check real quick to make sure that's on my list. Sure is. So let's start our synthetic division with the only choice I got. Boom, that worked. So this factors to x plus 4, x squared plus 9. Is everybody okay with how I factored this? Set this equal to 0. Apply the zero product property to set each factor equal to 0. And I have solutions of -4. And then to solve x squared plus 9, I could use the quadratic formula here, but like, come on, folks. We don't have to pull out that gun to kill this problem, right? I'm just going to do this directly. I'm going to subtract 9 from both sides, square root both sides, and squirting both sides, I get a plus or minus. Because I'm squirting a negative, I get an I, and the square root of 9 is just 3. So that's my 1 real, and this is my 2 imaginary. 2 because 1 for the plus and 1 for the minus, right? Let's do one more example and be done for today. Sound good? Okay, same kind of idea. Again, all the zeros. How many zeros should I be looking for? Who can tell me?
4.
4.
Damn.
There you go. What's my list of possible rational zeros? It's going to be factors of what over the factors of what?
4.
Nope. Factors of 35 over factors of 8.
It's all right if you want to go. I dumped this morning. Put a cookie up.
So far, so good? Now we're going to take a look at the calculator. So type that guy in. We'll go from -35 to +35. Take a look. Ooh, Boise, everything looks like right there by the x-axis. Maybe I'll just go from like -2 to 2 or something. Take a second look here. Well, this one looks like a half, right? You guys buy that? What about this other one, though? What does that one look like? Let me pull it back up. What does that look like? Just as a decimal. Like -1.2 or something, maybe? Let's look at our list. Is there anything I can make on this list that's close to -1.2? Oops. 5 over 4? 1.25? That's probably it, right? And 1/2 is obviously on that list. All right, what do you want to start your synthetic division with? 1/2 or -5 over 4?
Wow.
Yeah, I agree.
Yeah.
I'm going to write as a decimal though. Woo!
Wow.
So I have x minus 1/2 times 8x cubed minus 22x squared plus 16x plus 70. Oh, bugger, what happens here? Look at this. Do I know how to solve that? No. What are we going to have to do then? We're going to have to do a second synthetic division. Let's move. Oh boy, that did not do what I wanted it to. Okay. Ugh, come on now. Behave. There you go. So, well, the only other thing I can synthetically divide with is that negative 1.25. So here we go. Woo! So far, so good?
For the fractions, like at the top you've got x equals, can we just put those as decimals or like do you want to see?
So here's what I would say. If it's a terminating decimal, like 0.5, yes. If it's 1/3, an infinite decimal, you have to use the fraction, even in the synthetic division. But if it terminates, yeah, decimal it up, homie. Cool? All right. So what are we left with? I have a linear factor, another linear factor, and a quadratic factor. I'm good to go, right?
Yeah.
I want to point out something about this quadratic factor. Look at the coefficients. What do you notice? They're all multiples of 8. Let's factor greatest common factor of 8 out. When I do that, I'm going to push 4 into this one and 2 into that one. In doing so, I annihilate all of the fractions, which is kind of nice, but not necessary if you didn't do it. Everybody's okay?
You have to split the 8 up into.
I only did it to annihilate the fractions.
Okay.
I mean, you could put the 8 out here and it doesn't really make any difference. I just don't like fractions, you know? It's nothing personal. Oops, that was plus, so that should be minus. And then this guy needs the quadratic formula. And that's not supposed to be an 8, but rather a 4. Great googly moogly. All right, so negative of negative 4 is 4, plus or minus 4 squared is 16, minus 4 times 1 times 7 is 28, 16 minus 28 is negative 12. The square root of negative 12 is 2I root 3. And I can reduce the 2's to give me just 2 plus or minus I root 3. So I have 1 real here, 1 real here, and 2 imaginary there for 4 total, and I am dunzos.
Dunzos.
All right. You should now be able to do 13 through 14 as well as 20 to 53.
Oh, no.
Here's the good news, though.
It's due the week after.
Also, what's your assignment for the virtual day? Work on this.
Wait, so this is not due Sunday?
No.
Oh.
Bam!
Okay.
Not due Tuesday.
What would be due Sunday?
Delta Magnus.
The previous problem set like 1 through 19-ish minus the 13 through 14, and the delta math is for Sunday. What do you expect next class?
Homework quiz.
Homework quiz.
On this stuff or no? Because this I don't.
On the first lesson.
Okay. This is just a review of algebra. I didn't really do all that. I'm just kidding. Don't worry.
It's okay if you didn't do well. Ask some questions. I'd be happy to help you. I mean, I ripped through this today because, one, you guys all seem really disinterested. So it's like,
Math at the end of the day.
I understand.
It is so hard.
It's just, I'm so tired.
Especially after lunch, like I'm not dying. I'm just dying.